Ashley Coe in my experiment with a methanol water system on the distillation column. So here's the outline. We'll hit up the introduction, talk about reflux ratio, theoretical stages developed from McCabe field diagram, tray efficiency from that, tray temperature phenomena in this system in comparison to just a pure water system, the heat lost from each tray and removed by the condenser and stuff, and then talk about everything that we've covered thus far. So introduction to the experiment, we used methanol and water. So it's 31 mole% methanol, 69 mole% water. We set our reflux to 100. I think this is the last 100% reflux experiment that we've done. We started off at 24,000 watts just to get the system boiling, and then decreased it in kind of random increments all the way down to 400. So reflux ratio is based off of L over D, so the reflux stream divided by distillate stream. So at 100% reflux, this is also called total reflux. We're basically taking everything that gets condensed and putting it back into the column instead of it going out and into collecting in the distillate. Why do we do this? Because this determines the minimum number of theoretical stages, and this also gives us the tray efficiency. All right, so to find XB and XD, the mole composition in your bottom and the mole composition in your distillate, with 100% reflux is a little tricky. So what you do is at the end of your experiment where you want to see the theoretical stage, you take your tray 1 and tray 12 temperatures, which is the bottom temperature and top temperature, and then from the Van Laar diagram that we've constructed in distillation class, for those of you that are in that, use that temperature to find the mole% of methanol. So at the end of the experiment, we got down to 600 watts, then I dropped it down to 400 watts. But right here, tray 1, which is the top tray, had 63.4 degrees Celsius, which means it was 100% mole% of methanol. Tray 12, which is that bottom tray right above the reboiler, it was at 87.3 degrees Celsius, and so that shows us from that Van Laar diagram that there's 11 mole% methanol. At total reflux, constructing the McCabe field diagram, your operating line or your equilibrium line is your separating line. And you'll see that right here. So typically in a McCabe field diagram, you'll have like a diagonal line, and then this is your equilibrium line, and then you usually have a rectifying and stripping line, which are based off like your feed and stuff. But in this we have no feed and 100% reflux, so this is the line that's based off of. So if we start up at the top and draw lines out horizontally and vertically, this tells us the number of trays we have. We start from that bottom mole composition of methanol to the distillate mole composition of methanol. So counting this, it's 1, 2, 3, 4, 5, 5.8. So our theoretical stages are 5.8. The trays that are actually in this distillation column are 12. So to find tray efficiency, you just divide your theoretical trays by your actual trays, multiply it by 100. So at XB 0.11 and XD 0.99, our efficiency was 48%. From a previous pure water system distillation, you can see that when the power is dropped from 12 to 650, this is just the beginning of it. Didn't have one that brought it all the way out, but each tray drops kind of systematically and instantaneously with the drop in wattage from the reboiler. So if this was to continue out, you would see these all drop with the same, you can see that they're all have like the same slope, I guess. Something like that, but they're all like right above each other in unison. You'll see tray 1 drop, then tray 2, then tray 3, from the top to the bottom of the column. But in this experiment with methanol and water, you can see that these are the wattage supported by the reboiler. You can see that when we drop from like 2,000 to 1,800, like the upper or the bottom trays, this is tray 11 and tray 10. This is tray 12, and that's the reboiler up here. You can see like they don't all drop at the same time or same rate. You can see like little changes here. So this is the phenomena we're about to figure out, discuss. The cause of these temperature drops is because of the liquid-vapor equilibrium on each tray. So when you have a higher concentration of methanol on a tray, its boiling point is 64.5, I believe, while water's is at 100. So the temperature up here is going to be much smaller if you have more methanol in it. So this is composition versus time. So this is going to be the mole percent of methanol versus time. And these are tray 12, 11, 10, 9, 8, and 7. So you can see that when you change changes with composition are not instantaneous, they take time. So this is from 55-ish minutes to 90 for tray 7 to reach 100% methanol composition. You can also see that tray 7 changes much less than tray 12, or much more than tray 12, sorry. This is the drop from 16 to 800 watts. So tray 7 has already reached 100% mole composition. Tray 8's working its way there. And you can see this slope in tray 9 compared to the slope in tray 12. So tray 9, which is higher up in the column, is actually changing way more than tray 12, which is composition at the bottom of the column. And this is one more of those graphs, and this is the drop from 700 to 600 to 400 watts. So tray 7 and tray 8 have now reached 100% mole composition. And then you can see that tray 9 reaches 100% mole composition, but tray 10 and tray 11 just barely reach it here at the end. Tray 12 never even got to it. So why do these drop? It's because with 100% reflux, that methanol is coming right back down into the trays. So as wattages are decreased, more and more methanol will fall down. And that's right, why this temperature is so much higher than tray 1's temperature. All right, so the last thing is the heat. And we're really more analyzing this from the 800, 700, 600, 400 wattages. This is the cooling water graph produced from the distillation column program. To calculate heat removed by the condenser, you need this equation. This is the heat capacity of what's in the system. Let's go a little splinter. And the flow rate. And then this is the temperature of the cold water return subtracting the cold water supplied. You get that difference right here. So you can see that at like 2,000 watts here, our change in temperature is way more. So our heat removed by the condenser is going to be way more. And then close to here, this is about 700 watts right here. This change in temperature is very small. And then as we even decrease to 600 watts, to 400 watts, it actually even falls on the same line here at 400 watts, which indicates that the condenser is removing no heat. So at 800 watts, the condenser, using that equation, that calculation, the condenser roughly removed 200 watts, And at reboiler power of 700 watts, the uncertainty was so low, or so high, that it's almost negligible. But the uncertainty tells us that it could be removing up to 100 watts, but definitely less than that. So this is a schematic of the column with the heat loss of each component. So if we plug 700 watts into the reboiler, and since that heat removed, the uncertainty was so big, it's going to be less than 100. So that's basically 0 watts since it's negligible. So if we have 700 watts coming in, and the drop from 700 to 400 watts, all the trays dropped off as well. So we can see that right here. That's 700 watts to 400 watts right here. There was all the trays have dropped off. Since the condenser is removing no heat at 400 watts, we know that, I keep saying 400 watts. At 600 watts, the condenser is removing no heat, so we know that none of the trays are still fully heated up by 600 watts. So if we plug in 700 watts to the whole column, we know that there's 500 plus or minus 100 being lost by the reboiler. Since at 400 watts, the whole column is not heated anymore. And that means there's 200 watts being lost by the whole column. And using suggested percentages of heat loss from Dr. Henry, these trays are insulated and these trays are insulated, but the feed and the reflux are not. So that's where your biggest heat losses are going to come from. So taking it out of this 200, the reflux loses about 80 watts. The feed's losing about 80 watts, and then each tray is losing about 3 watts. So in overview, so why do we use total reflux? Is to determine the minimum theoretical stages for design. We found the tray efficiency for the distillation column was 48%. And we know that tray temperatures change based off that mole composition of the lighter component, methanol in our case. And then we know that the column requires 800 watts to condense and collect distillate. So you need at least 800 watts in any system if you're actually going to be separating the system. So that's it. Does anyone have any questions?